Good morning, curious minds. If a tree falls in a forest with no one around, does it make a sound? Actually, no, because sound needs a medium. When an object vibrates, it shakes the particles of air around it, and those particles bump into their neighbors to carry the disturbance forward. The speed of this wave depends on the medium's density and elasticity. Finally, when these vibrations hit your eardrum, you hear sound. It's just like a stadium wave, each person stays in place, but the ripple moves across. No air, no particles, no wave, which is why space is eerily silent. Our ears are selective listeners, tuned to catch only vibrations between 20 Hz and 20,000 Hz. This is called the audible range. Anything below 20 Hz is infrasonic, anything above 20,000 Hz is ultrasonic. Fun fact, hearing fades with age, especially at high frequencies, so that buzzing mosquito ringtone your kids complain about might not even register with you. Dogs, however, hear ultrasonic sounds easily. Dog whistles are proof. So while we hear music, dogs sometimes hear the hidden tracks. Now let's decode two important properties, amplitude and time period. Amplitude is the maximum displacement of particles from their rest position. Greater amplitude means louder sound, so when your neighbor blasts their speakers at night, blame amplitude. The time period is the time taken for one complete vibration, measured in seconds. And here's the golden relation, time period equals 1 divided by frequency. In short, the loudness of sound depends on amplitude, while the speed of vibration is determined by time period and frequency. Next up, frequency and wavelength. Frequency is simply the number of vibrations per second measured in hertz, and it depends only on the source. Wavelength, represented by lambda, is the distance a wave travels in one complete time period of vibration. The relation is frequency equals 1 divided by time period, which shows that frequency and time period are always inversely related. Imagine a guitar string, pluck it faster, and the frequency increases, the wavelength adjusts accordingly. But here's the key point, frequency comes from the source, not from the medium. Now let's tie it all together with the wave equation. The distance a wave travels in 1 second is called its velocity, v. The fundamental relation is velocity equals frequency multiplied by wavelength. In a given medium, the velocity stays fixed. So, if the frequency goes up, the wavelength must shrink to keep the product constant. That's why higher-pitched sounds have shorter wavelengths when traveling in the same air. It's just like runners on a track. If you take more steps per second, your stride length becomes shorter, but your overall running speed can still remain the same. Suppose a sound wave has a frequency of 200 Hz and a wavelength of 1.7 meters. Using the relation, speed equals frequency multiplied by wavelength, we substitute the values 200 multiplied by 1.7, which equals 340 meters per second. And there it is, the wave velocity is 340 meters per second, which matches the standard speed of sound in air at room temperature. Notice how neat this is. The formula connects all three quantities, frequency, wavelength, and velocity. So once you know any two, you can always calculate the third. So, let's wrap it all up. Sound waves always need a medium and travel through the vibrations of particles. Our ears can hear only the range between 20 Hz and 20,000 Hz. Anything below that is called infrasonic, and anything above that is ultrasonic. The amplitude tells us how loud a sound is. The frequency decides its pitch. And the velocity is linked with wavelength through the relation speed equals frequency multiplied by wavelength. Also remember, frequency and time period are always inversely related. Frequency equals 1 divided by the time period. Put simply, If you know these three buddies, frequency, wavelength, and velocity, you can describe any sound wave completely. And with that, you've just tuned into the science of sound itself. See you in the next session with more physics magic.